will resume with the last talk of this morning. We have Sven Polak, who is a postdoc at CWI. And please, the title is on crossing numbers.
Thank you, Evelyn, for the nice introduction, and also thanks to the organizers for this wonderful conference. So I will speak about lower bounds on crossing numbers of the complete bipartite graph. And this is joint work with Daniel Roche, who is also in the audience, and he is at University Klagenfurt. So crossing numbers of the complete bipartite graph. So we have m points on top and we have m points below, and we connect them all. And how can we do this? And how can we draw this in the plane in such a way that the edges cross as few times as possible? And this is a problem which goes back to Turan in the 1940s. During Second World War, he had to do forced labor near Budapest in a camp, and he had to work in a brick factory. And in this brick factory, there were mines, and there were storage facilities outside the mines, and there were ovens inside the mines. And all the ovens were connected with all the storage facilities by railway tracks. But when there was a crossing between two railway tracks, the minecart could fell off the rails, and then the bricks could fall out. And this was, of course, not good. So Turan thought about how can we optimize this number of crossings? How can we minimize this number of crossings? And this is where the problem is coming from. But also it has more modern applications. For example, in chip design, chip makers want few crossings. So if you have M transistors on a chip and N other transistors, how can you connect them in such a way that the connections between them cross as few times as possible? This is very relevant for chip design. And also we don't require the edges to be straight. So any curves are good. Yeah.
And when there cross many lines at one point, is this one crossing? Or
no, several crossings. Each between two edges, each crossing, you need to cut. And there's a conjecture about what this optimum number of crossing is. And this is by Zarankiewicz. So he conjectured that the optimal drawing always looks like in the middle picture. So you draw the endpoints here on the line and other points on this line, and then you just draw straight lines. Then you can count the number of crossings you get. So if you take 2 points here and 2 points on top, together they induce one crossing. And if you make the count, then you get this number. And so we know you can do it with so many crossings. But the question is, maybe we can do it with fewer crossings.
So here, all of the lines are straight lines. Is it known that it doesn't matter what it is? Even if you don't know the conjecture, is it known that the straight lines or curved lines are the same?
No, in general, not. No. But the conjecture is that in this case, straight lines are always optimal. In this case, yeah. So the conjecture is that you can always draw it like this with straight lines, the minimum. So actually, Turan already thought that this was the optimum solution. But then Zarankiewicz thought he had a proof for it. But sadly, this proof turned out to be false. But now it's called Zarankiewicz's conjecture. Yeah, so we know we can do it with so many crossings, but maybe we can do it with fewer. And so what's the goal of this talk is to compute lower bounds on the crossing number. As a partial progress towards Zarankiewicz's conjecture. So of course we are at Poema, so we know the general methods to find bounds and approximations, linear programming and semi-definite programming. And I will introduce the bound by de Klerk, Mahari, Pasechnik, Richter, and Salazar, a quadratic programming bound. And then I will give the semi-definite relaxation, which they also came up with. And then I will speak about our work. So with Daniel, we compute alpha 10, which is one bound in the hierarchy of de Klerk et al. And then we use the symmetry to make the computations tractable. And for example, we found for K1010 a new lower bound of 388. And the old lower bound was 384. And the conjectured value, which is the Zarankiewicz number, is 400. If you draw this drawing, you have 400 forces. But we have lower bounds for many more instances. These are not the only instances. These are only a few examples. We also give a further relaxation because this semi-definite relaxation alpha m also turns out to be quite hard to compute. So we give a further relaxation beta m of this alpha m, and we can compute that up to a bit higher, for a bit higher m. So we will see that later in this talk. So first, a general slide about STP. I thought maybe I should remove this, but then Daniel said the pictures are nice, so show it. So of course, so everybody knows in the audience linear optimization, where you maximize a linear function over a region that may look like this, given by linear inequalities. Very classical method and very efficient algorithms exist for it. But more recent is the focus on semi-definite optimization. And also efficient algorithms exist for it in theory, also in practice, but there is mainly a problem that in practice, matrix size is still a limiting factor. So you're bound by the memory in the computer. And in this talk we will, because there's symmetry present in the SDP we will study, we can exploit this symmetry and give a block diagonalization with very large matrix and reduce it into many smaller matrices, of which it's easier to check positive semi-definiteness. And then we can give the program to an SDP solver, which then gives the solution. And the first SDP goes back to Laszlo Lovász for computing the Shannon capacity. And SDP has, of course, many applications. It's the only known way to color perfect graphs, for example, in polynomial time. And also the best approximation algorithm for max cut goes through SDP. So let me tell you about the lemma which underlies these bounds for crossing numbers. Okay, so we have again the bipartite, the complete bipartite graph KMN, and we put 1 up to M on top and B1 up to Bn on top. So these are the two sides of the bipartition. Now, given a fixed drawing of KMN, we define for each vertex Bi on the bottom, we define gamma Bi to be the cyclic order in which the edges from Bi go to the top part. So here we have vertex B1, and then the first edge goes to 1, then goes to 4, then to 5, then to 2, then to 3. So the order is 1, 4, 5, 2, 3. And this is a 5 cycle. So in general, an M cycle. So to each vertex Bi in one side of the bipartition, we associate an M cycle. According to this procedure. It's just a cyclic order in which the edges go to the 1 up to M. And now there's a classical lemma by Kleitman, and there's a nice proof in a paper by Woodall, that the number of crossings of edges incident with Bi and Bj. So you take any two vertices in the lower part. This is at least the minimum number of swaps of adjacent elements of gamma Bi to change gamma Bi into the inverse of gamma Bj. So gamma Bi and gamma Bj are both permutations, M cycles. So you can also compute the inverse, which is also an M cycle. And then the minimum number of adjacent swaps inside this gamma Bi to change it into gamma Bj inverse. This is this number. This gives a lower bound for the minimum for the number of crossings edges incident with Bi and Bj.
So you mean by just transpositions?
Transpositions, yes, of adjacent elements. But you can also swap the first and the last element, so it's a cycle. So yeah. Maybe it's good to see an example. So here we have again the vertex B1 from the last slide. So it has order 1, 4, 5, 2, 3. And now I also drew a point vertex B2, which has order 1, 2, 3, 4, 5. So gamma B2 is 1, 2, 3, 4, 5. Gamma B1 inverse is 1, 4, 5, 2, 3 inverse, and this is 1, 3, 2, 5, 4. And now we need to compute the minimum number of swaps of adjacent elements to turn gamma B2 to change gamma B2 into the inverse of gamma B1. And this is 2. Because if you swap 2, 3, then you get 3, 2. And if you swap 4, 5, you get 5. Maybe better to see it like this. So according to the lemma, there are at least 2 crossings inside this picture. And you see them here. So this lemma, which I won't prove here, but you can use this to give lower bounds on the crossing number of the complete bipartite graph. And this I will show now. It's method by de Klerk et al.
Sorry, but when you draw straight lines and this you cannot achieve it, right?
No. Well, maybe you can, but then maybe you need to move the vertices in another way. Yeah. Money? So we denote in this talk, we let Zm be the set of M cycles. So it has cardinality M minus 1 factorial. And we let Q be a very large matrix, size Zm times Zm. So size m-1 factorial by m-1 factorial, indexed by Zm. And we put an entry sigma tau, we put this number, the minimum number of swaps of adjacent elements, we change sigma into tau inverse. The minimum number of swaps of adjacent elements of sigma to change it into tau. And then we can get a lower bound on the crossing number of the complete bipartite graph. So if we have an optimal drawing, then we take the gamma from this optimal drawing. So to each vertex bi in one side of the bipartition, we associate an M cycle. Then the crossing number is the number of crossings in this drawing. This is at least this sum over all distinct pairs of Q gamma bi gamma bj. Yeah, because for each pair bi bj, we know that the number of crossings of edges of bi and bj is at least Q gamma bi gamma bj. This is the lemma on the last slide. And now if we just sum over all adjacent pairs, then we know that the total number of crossings in the picture is at least this sum.
Does anything depend like on gamma or like on ij? Like does gamma depend on ij, or it's universal for all like pairs?
So we fix an optimal drawing.
Okay.
Yeah. So we have an optimal drawing, and then we can extract the gamma from it. Yeah. And yeah, gamma then depends also indeed on I and j. Yeah. It depends on the drawing.
But like if I allow different like gammas like for a pair of I and j, can I get a larger?
If you allow different, you can get larger, but we now fix a optimal drawing.
Okay.
Yeah, and take just the gammas from this optimal drawing. Okay, then there's another fact which we will need in the proof, but which I will not show right now because yeah, we have limited time. But as it said, Q sigma sigma is this value. It's this 1/4 m-1 squared and then rounded down. So then there's a theorem. So by the Clark et al. Is that so we define Qm to be the following quadratic programming parameter. It's the minimum x transpose Qx, where x is a non-negative vector of size Zm, and all the entries of x sum to 1. So 1 transpose x is 1. Yeah, so it's optimization problem over the standard syntax. And then the lemma is that the theorem is that the crossing number is at least, well, the expression you see here, the half n squared Qm minus this vector. It's nice maybe to see a proof. So again, we assume that we have an optimal drawing. Now we let C be the vector, very large vector indexed by all M cycles. And we put C sigma to be the number of bi with gamma bi equal to sigma. So for each M cycle sigma, you just count the number of bi which have sigma associated to it via gamma. So
it has nothing to do with the other.
no problem, no problem. So in total, the entries of C to which number do they sum? Maybe somebody sees it. Maybe I'll say it. So the vector C, if you sum all the entries, it sums to n, because in total there are n bi's. Yeah. So if you sum all the entries of C, then it sums to n. So if we now just take n inverse C, then it's feasible for Qm because it sums to 1. And it's also entry-wise non-negative because yeah, all the entries of C are non-negative. So now we just compute n squared Qm. This is n squared x transpose Qx, which is C transpose Qc. And we just write out the sum. It's the sum over all sigma tau in Zm, C sigma, C tau, Q sigma tau. And now, yeah, we write this sum in a different way. We now go not over all sigma tau in Zm, but over all I and j is 1 up to n. because C sigma just counts the number of bi with gamma bi is sigma. So you can rewrite this set. And now, now we split this sum into 2 times because the matrix Q is symmetric, we split it into 2 times the sum over all dipping pairs and plus the diagonal. So here I just do nothing basically. It's just splitting it into two parts, the off diagonal and once the diagonal. And now we use this lower bound here that the crossing number is at least. If you take the off diagonal and you sum it, then the crossing number is at least this value. So 2 times the crossing number is at least this term. And then we use that the diagonal of this matrix is known. So here you just get n times this value, and then you're done. But this is how this quadratic programming lower bound is derived. Questions? Good. Well, maybe not so good because it's still hard to compute this parameter. So we want to go to consider relaxations of this parameter. So again, so here is again the parameter. And now we consider a semi-definite relaxation alpha m of this parameter qm. And now we just compute the minimum of the inner product of x and q, where x is a matrix indexed by zm, entry-wise non-negative. Inner product with the all ones matrix is 1, and x is positive semi-definite. And it's not so hard to see that this is a lower bound on qm, because if you have any optimum vector x here, then you take just the outer product of x with itself. So you take the big matrix x becomes small x times x transpose. And then this x transpose is entry-wise non-negative because x is entry-wise non-negative. All the entries sum to 1 because this is the case for the small vector x. And this x transpose is positive semi-definite because it's a rank 1 matrix. And also the objective value of x transpose, the inner product between x transpose and q is equal to x transpose qx. So the objective value here can only become smaller because you take the minimum over because any optimum value, any optimum x here gives a feasible x here with the same objective value, and so this minimum can only become smaller. Yes.
Q dense or sparse?
So Q is dense, but this has a lot of symmetry. So basically almost all entries are non-zero of Q. Except if sigma is equal to tau inverse. Good. So it's nice. Now we have a semi-definite relaxation, but still there's a problem because this set Zm is very large. It has cardinality m-1 factorial. And this, it grows very large. It grows very fast. So we want to exploit the symmetry to compute this parameter. And we consider the following group Gm, which is the direct product of Sm with the abelian group of order 2. And Gm acts on the set of m cycles. So you can, if you have an m cycle, you can conjugate it with an element of Sm. Conjugation preserves the cycle type. And also, if you have an m cycle, you can invert it. Then you also get an m cycle. And you can prove that the matrix Q is invariant under the simultaneous action of Gm on the rows and the columns. And then you can use that to show that you can restrict the search space to the algebra of Gm invariant matrices, where Gm acts simultaneously on the rows and the columns of X. And then it's a classical result by Artin-Wedderburn that there exists a block diagonalization of this algebra. So yeah, I will show that in a later slide in more detail. Oh, but yeah, to give any idea of the number. So for example, for n is 10, first we have n minus 1 factorial is 300,000, 360,000 something. And then if we apply the reduction, the maximum block size only becomes 38. And the sum of the squares of the block size becomes this now. Sadly, after reduction, it will still grow exponentially, but we can put more in the computer. Okay, now a bit more in detail. So let G be a finite group acting on a finite set Z. And now we decompose the vector space C to the Z as follows. So V is C to the Z. And we decompose it into irreducible G modules, such that Vij is isomorphic to Vi prime J prime if and only if I is equal to I prime. Yeah, the number K and the is unique. And also the MI are unique, and the inner direct sums are also unique, but the Vij are in general. And now, yeah, so what we do now is from each irreducible module Vij, we take one vector Uij, and all these chosen vectors also need to satisfy a certain property. Namely, that if you take isomorphic copies, Vij, Vij prime, there should be a G isomorphism between them, which also maps the chosen vectors to each other. This is the condition which we require to the Uij. And then if we define the following map, which goes to from the set of G invariant matrices in CZ times Z to this direct sum of full matrix algebras. And it just maps a matrix A to the direct sum of Ui star A Ui, where Ui is a matrix where you group these Uij together. For a fixed I and J goes from 1 to Mi. And then for any matrix A which is G invariant, we have that A is positive semidefinite if and only if the image is positive semidefinite. And we can use that in our reductions because the sum of the Mi squared is generally much smaller than the cardinality of Z. If the group is large. And yeah, just some terminology. We call this set of matrices U1 up to UK, which we obtain in this way. We call this a representative set for the action of G on V. And now what we used in our reduction is the following observation. So suppose that Gx on complex vector space, yes, G is a finite group, complex vector space is V and W, all finite dimensional, and that F from V to W is a surjective G homomorphism. Then, so the informal observation is if we have a reduction for the action of G on V, then we can obtain from this a reduction for the action of G on W. But maybe more in detail. So if we have a representative set for the action of G on V, which is as in the previous slide, is the set of matrices U1 up to UK. And now we let Ui prime consist of a minimal spanning set among the images of Uij, so we can map these Uijs with this matrix with this map F to W, and then we just take a minimal spanning set among the Fuij for a fixed IN, where J goes from 1 to M. And we put them together in a matrix. Then we proved, well, it's basic, it's I think it should be known, but it's that this set is a representative set for the action of G on W. And we could use that in our reduction. So maybe, so I will show it now. So what we really did into deep in high level steps. So we start with the permutation module M1 up to M. So this is a partition for SM. So for the ones who know representation theory of the symmetric group, they know that the decomposition of this module is known. So we have that in the literature. So we can just get the vector Uij for this permutation module M1M from the literature. And then we observe that there is a surjective SM homomorphism, so a surjective linear map, which also respects the group action from this module to CZM, which is the module we are interested in, and which maps a tabloid. So a tabloid is a row equivalence class of a Young tableau. So M1M just consists of all formal linear combinations over C of Young tabloids of a certain shape. The Young tabloids are the basis elements. So which maps this tabloid to the indicator vector in CZM. Of this M cycle. And then we apply the map F, and for each I we just take a minimal spanning set among the images. And you can just do that with linear algebra on the computer. And then you find the reduction for SM acting on CZM. And this is almost what we need. Oh yeah. Then there's also a promotion of Daniel Brosch's thesis. It's a very nice thesis, and also he considered flag algebras, and there are always modules. So MU are permutation modules for the symmetric group, and when they're and then he has a good algorithm for when there X group on the rows of such a permutation module. Then you can also find block diagonalizations for these cases, and he has a fast algorithm for that. And basically, this is a special case of that, because you can see that M1 of 2M, this is it is basically, if the cyclic group acts on it, then you and you take all the equivalence classes under the cyclic group, then you get the CZ. And so we also have a ±1 action, but we observe that these two actions they commute. So the SM action and the inversion action, they commute. So we can apply this ±1 action just later, and it splits each block into two. But for details, you can look at our paper. So this is basically high level the overview of what we did to obtain the block diagonalization. So now up to the results. So what has been done? So the Clerc et al. They computed alpha 7 and they introduced this whole bound. And Dobre and Vera, they computed a better lower bound on Q7 by using approximations of the copositive cone. Then the Clerc, Pasechnik, and Schrijver, they exploited already some symmetry to compute alpha 8 and alpha 9, but they didn't exploit the full symmetry. And then with Daniel Brosch, we compute alpha 10 using the full symmetry. So here you see how the sizes compare. So after the reduction of the Clerc, Pasechnik, and Schrijver, the number of rows becomes the number of GM orbits on Zn times Zm, where Gm acts simultaneously on both copies. And in our reduction, the number of the squares of the block sizes becomes this number. So basically square models. And we also give a lower bound beta m on alpha m, and we can compute that for m up to 30. And I want to tell a bit about this lower bound. So if we have the block diagonalization, then we have already reduced the program a lot. And we require that all those blocks are positive semi-definite. But we can also just require that only one small block is positive semi-definite instead of all the blocks. Because we take a minimum, if we require that only one of those blocks is positive semi-definite, we have less restrictions, so the minimum can only become smaller. So if we only require one block to be positive semi-definite, we get a lower bound. And there turns out to be one block which works very well. And it's the blocks which correspond to this irreducible representation of the symmetric group. Here you see the partition. And this block has size, it's linear size in M, it's very small. And it gives a good lower bound on alpha M. And did we saw this, that is a good lower bound. We saw this just experimentally from the values we compute. And how could we compute beta? We could compute this up to m is 30. So beta m has few variables with very small matrix blocks. So we went to the dual, then we have Q variables, a very small matrix block with many linear constraints. And so what we did is we solved the program first just without constraints, and then checked which linear constraints is violated the most. Then we added this to the program. And then again, we checked which linear constraint is violated the most, and we add this to the program. And this procedure, this ended in like 100 steps. Well, the number of constraints is a million or something. So in this way, we could, compute up to MS13. Yeah, maybe it's nice also to see the dual. So it's just a maximum T, where Y is a matrix of size n-1/2 times n-1/2, and which should be positive semi-definite. And for each orbit in Zm times Zm, so G and X simultaneously on those two copies of Zm, and then you have the orbits. And for each orbit, there is a linear constraint. And Q omega is just the value of the matrix Q on this orbit. And A omega is a matrix which follows from the symmetry reduction, but I will, maybe it's, I wrote it here, but it doesn't matter exactly, but this A omega follows from the symmetry reduction, and the rest, are all things which are defined. And what we observed also is that the beta M, the optimum solutions, if we compute them, they have very low rank. So, for example, for MS13, we the rank is only 1, and so here we see the vectors Vm such that the optimal Y is we have some scaling is Vm transpose, and here we just plot the coordinates of this vector Vm. So for P13 there are 30 minus 1 divided by 2, 6 coordinates, and we plot them here in the. There seems to be some structure maybe, but this is for further research. Good. Now up to the computational results. So we have new lower bounds for many instances. So I showed already this table. So for K1010, for example, we have a new lower bound of 388. But for all KMN with M and N at least 10, we have new lower bounds. And for example, for K13 and the previous value was 8.37 something n squared, and we improve it to 8.65 something n squared. And also, so if you have a lower bound for the crossing number of KKM with and you have M which is larger than K, then the crossing number of KMN is at least this value here, because KMN contains n choose K copies of KKN, and each crossing of KMN is contained in n-2 choose K-2 of those copies, because it's determined by 2 points out of n. So if you didn't see this directly, it doesn't matter, but the point is that you also can get lower bounds on the crossing number of KMN for n larger than 13 if you have those lower bounds, by just applying a double counting argument. Also can get asymptotic results out of it. So the Clerk et al. They proved already this relation, that so Zn is the conjecture value, this is on the Jacobs number, and this is the crossing number, and that the limit of n to infinity, this is at least this value here. And so we computed 8 alpha k divided by k minus 1, we get those values, and 8 beta k divided by k minus 1, we get those values. And the boldface values are the new values. So these are, for beta, everything is new basically. For alpha up to 9, it was already computed. But the question is, so maybe this limit goes to 1. And it would be nice if these bounds go to 1. So this is also nice for further research to find out if this really goes to 1. So here they are plotted. So Etienne de Klerk thought that it would not go to 1. And I think, Daniel, you thought that maybe it would go, right? And I don't know. But sadly, this is not the best asymptotic known lower bound. At least Noreen and Wolt, they claimed already that they have an asymptotic lower bound of 0.905. And they presented this at the conference, but they have no archive paper online. And we sent them an email, but they also didn't reply yet. But we will send them again.
Okay. How come the green numbers are better than the blue numbers? I don't know.
So this is because alpha k is stronger. Alpha k is original bound, and beta k is a relaxation of it.
Oh,
Because we only we put less constraints. We only
I see.
require a small matrix. But it's still remarkably close to it. Yeah, and also from our results follow also a bit. So not only if we go let n go to infinity of the crossing number of k and m, but also for each fixed m, yeah, we have an asymptotic result, namely that if you let n go to infinity and you fix m, that you have this asymptotic load. So this is new. So to summarize, semi-definite programming gives good lower bounds on the crossing number of k and m. So the key contributions is a symmetry reduction and a new relaxation beta m of alpha m. The advantage of the approach is that it's only based on m cycles, so you basically forget the whole problem, but you only look at the m cycles. This is different from flag algebras, maybe. And yeah, for further research, it's still an interesting question. Maybe it's possible to give the optimum solution to beta m analytically, because yeah, they have very low rank, and there seems to be structure. Thank you for your attention, and I look forward to your questions.
Are there graph classes where you could apply something like this?
Interesting question, but yeah, it's hard because you need to figure. Yeah, we really use that we fix one side of the bipartition, and then so we don't know. Maybe multipartite graphs. We thought about that a little bit. Multipartite complete graphs. Yeah, but this is also interesting for further research. Yeah, Gordy.
On the last slide, that you wrote,
This is the last slide.
The last number on the right-hand side on the table, the 0.8878.
Yeah.
I guess it's not a coincidence that it coincides with the asymptotic.
Yeah. This is where this asymptotic bound comes from.
So is it?
It's
Is
just
it stagnant at from level 13 on?
what? Yeah, so we also have a bound for each m at least 12. We can put this constant here, and then we have also a result.
That's what it says.
Yeah. Money? Yes, they stay all below it. Maybe for m is 4 not or something. So for small m it coincides, but for m is 5 it's already different. So we know that it's not exact for so Etienne already knew that it was not exact for like m is 5 or m is 7. But maybe if m goes to so the qm is still above this green line. So maybe this qm goes asymptotically when m goes to infinity. Yeah, it goes to 1. Yeah, we don't know.
So it's not exact, also not after rounding.
Also not after rounding. It's not exact for small instances.
So there's the question in the back.
Yeah, so maybe from the incorrect proof, can you get some analytic bounds in lower bounding?
I don't know you mean the incorrect proof from Zarankiewicz?
Yeah, so they were saying that was the boundary 5, but maybe.
Yeah, I should maybe look at the original paper because I don't know the incorrect proof. It was shown to be incorrect.
I think we completed the questions, so thank you very much.
Thank you.
See you all this afternoon.